everyone, and welcome back. My name is Mr. Kovault, and in this video, I'm going to be going over density and applying this to Earth examples or geography examples or examples involving the Earth. So let's get into this. So what you see in front of you are two Coke cans. You have Diet Coke and you have Coca-Cola, regular Coke. So then the question here is, why is one floating and the other is not? So why is that? Well, as you may have guessed, if one is floating and the other one is sinking, then that has to do with the density of each can relative to water. So why would a Diet Coke be less dense than the regular Coke? So we see that the Diet Coke is floating in the water, so it's less dense than the water, but the regular Coke must be more dense than the water since it's not floating in the water. So then why is that? Well, one of the reasons is the amount of sugar that is in each can, right? More sugar means more density. So you could see that the regular Coke is more dense. It has more sugar. So that is part of the answer. So let's keep going. Well, density. What is density? We got to know what that is. So density is how much stuff is crammed into how much space. And the stuff we're going to call matter, right? Or the stuff that has mass, right? So if you can fit in more matter or stuff into a certain space, that's going to make it more dense. And the space that we're talking about is volume, right? How much can you fit into a particular amount of volume? Okay, that is density. So density is usually used for solids and gases. It's also used for liquids, of course. So we're thinking about the idea that the how much stuff part of it is one part of density, right? And the crammed into, like we're going to cram that stuff into a certain amount of space. So if you think of it like how much stuff is crammed into how much space is volume, how much stuff is matter or mass. So how much stuff is going to be what we're talking about with regard to mass. And the crammed into, like how much we can put into, is going to be like the per part, and we'll see that in a moment. And how much space is what I said with regard to volume. So it's going to be mass per volume. So density is mass per volume. The per means that we are dividing mass over volume, mass per volume. So you could use different units for this, right? So mass is normally measured in grams. So you can see here grams. And then volume is often measured in milliliters. It could also be measured in liters. So it just depends on what mass unit or what volume you want to use. And there's other units you could use for each of those. Like, for example, instead of milliliters, you could use centimeters cubed, right? 1 centimeter cubed is equal to 1 milliliter. So you could have grams per centimeter cubed. This is often used for solids. If you see grams per centimeter cubed, usually that's the density of a solid. If it's a liquid, usually that's going to be grams per milliliter. And then, of course, we have kilograms per liter, right? So this might be for a liquid. It could be for a gas too. So kilograms is another unit of mass. So again, we have mass per volume. Here the volume is liters. So this could be a gas. We can usually measure in gas, but if it's gas, it probably wouldn't use kiloliter or kilograms. So this might be a liquid. So these are different units you could use to measure density. Again, it's mass per volume in grams per centimeter cubed, and kilograms per liter. So, etc., etc. So again, as I said before, you want to remember that 1 milliliter is equal to 1 centimeter cubed. That's true by definition. So always remember that. So if you have something in centimeters cubed and you need milliliters, it's the exact same thing. So if you have 30 milliliters of a substance, then you can rewrite that as 30 centimeters cubed. Okay, what's the density equation? As I said, it's mass per volume. So if we write that as an equation, density is equal to mass over volume. So the question then becomes, let's put this to practice. So which one is more dense? If we're thinking about this in terms of how much stuff you can cram into a space, which one would it be? The left one or the right one? If you said the right one, you would be correct. So this is more dense because look at the boxes. These are the same volume, same space, but obviously this one has less particles, less stuff in the space, and this one has a lot more stuff in the space. So this one is going to be more dense. Okay, now here we're looking at two different volumes. So here, this one is a smaller volume, and if we look at the number of particles, this has 7 particles in there, and this has 1, 2, 3, 4, 5 particles. So this is a bigger volume, right? But in addition to that is less particles, so this one is obviously less dense than this one. So if you said the right one, or I'm sorry, if you said the left one is more dense, you would be correct because we're cramming more particles into a smaller space. So this is like if you decrease the volume on the bottom of your equation, you're going to cause the density to go up. If you increase the top part, the mass of your equation, the density is going to go up as well. So here's an example of density of liquids. It's just not solids. You can have density of liquids. You can actually make this density column at home. You can just find a bunch of stuff at home, right? Honey, corn syrup, maple syrup, milk, dish soap, water, vegetable oil, rubbing alcohol, and lamp oil. You could find a lot of this stuff and you could just mix it together really quick, carefully, or you can mix it together and let it sit for a little while and it will separate, and then you could put things into it and see which layer does it stop at, or does it stop between layers, right? So you could have a dice. So here we have a die that's been put in there. Here we have a bolt. The bolt is pretty dense, so it's going to sink all the way to the bottom. The die is somewhere in the middle. Here we have a bead. A ping pong ball is not very dense at all, so it's going to lay on top. And you can see that the layers, each of these different substances, are separated by their density. The higher you go up, the lower the density. The lower you go down, the higher the density. So I hope this is helpful. Okay, so you want to memorize this. Density of water. What is the density of water? It's 1 gram per milliliter. That is the density of water at room temperature, of course. But this is something that's going to be useful, and you want to remember that. So memorize it. 1 gram per milliliter. That only applies to water. So that's the density of water. Know it. Or you could say 1 gram per centimeter cubed. And this makes sense because, This makes sense because we said earlier that 1 milliliter is the same as 1 centimeter cubed. So you could write 1 gram per mill or 1 gram per centimeter cubed. Okay, what about the density of air and air pressure? So this is very common experience. So we experience this fairly often, especially if you're flying. If you fly or have flown before, you've probably noticed this. So the air, the atmosphere that we live in, is broken up into levels, and you can see that as you get far closer to the sea level, the particles are more bunched together. So that means you're fitting more particles, more stuff into a given space. And so we have a higher density of air particles. So the pressure here is larger. Pressure is dependent upon the amount of particles that are bombarding you, that are hitting up against you. So down here at sea level, if you got a whole bunch of particles, that you got more particles uh, bouncing off of you, causing pressure. But as you go up, the number of particles decreases in the given space. And so less particles means lower density. Lower density means, of course, the fewer particles you have, the fewer that are bouncing against you, pushing on you and creating pressure on you. So when you go flying in an airplane, as you ascend, you'll find that your ears pop and you feel this pressure difference in the eardrum. That's because the outer ear pressure is decreasing, but then the pressure on the other side of the eardrum is kind of staying the same. So eventually it'll pop, allowing the pressure to equalize on both sides of the eardrum. And the same thing happens when you are descending. Okay, so here's another picture. So again, you look at how few atoms are pressing down on the guy at the top of the mountain. So here you're at the top of the mountain, and then you see you have less particles up here. So less particles are pushing against this person here, so they feel less pressure. And then the person down here, much farther at the base of the mountain at sea level, they have more particles pushing against them, so they're going to feel more pressure. And again, you don't really notice this in everyday life, right? It's only when you change your height that's when you're going to start to notice it. So if you going hiking up a mountain or you fly in an airplane, you'll notice at that point the change in air pressure. All right, what about layers of the earth? We talked about pressure in the atmosphere and how the density changes in the atmosphere and the air around you. Well, what about the layers of the earth? There too, we have different densities occurring. So there are different densities that lead to the earth have different layers. So here are the different layers of the earth, right? They're breaking up into different layers. The most common layers that we know are the crust, the mantle, the outer core and inner core. And the mantle can be divided also into the upper mantle and lower mantle and things like that. So here, with regard to the earth layers, again, as you go closer to the surface, closer to the center of the earth near the core, you get more and more dense. There's more and more pressure there than at the outside. So you're cramming more substance into a certain space. So, and that has a lot to do with gravity. Gravity is a lot stronger as you get closer to the center of the earth, and that gravity is acting on all the particles, kind of bringing them kind of closer together. And also, you got all this stuff on top, right? All of this layers on top pushing against the layers on the inside, crushing it, bringing it closer together, packing it more closely together. And so you get more density on the inside versus on the outside. And so this means that you can get certain activities like earthquakes and volcanic activities. So you have the density of the crust, right? You got denser plates, right? You got these tectonic plates that are, floating on top of the mantle, the upper mantle, and so the difference in the density of the plates will determine like how the plates are going to interact or react when they come together. So here you can see that this plate here you have more dense, and so that's going to end up going below. So you got what is called a subduction zone here, And so this is going to be pushed underneath while this plate here stays on top. And this creates a trench. This is the part of what might be the mid-oceanic trench. And so what happens is that up here, this gets hotter as you go down. The plate can melt, and so this creates magma. This magma is going to get hot and it's going to rise to the surface and then push up the surface of the crust, creating what we know are volcanoes. And so then the magma comes out in the form of lava, and we are familiar with that. So it's also why, if you look along the mid-oceanic ridge or where the different ridges are, you'll see along them a bunch of chains of volcanoes. And so you can see why that is, right? So this is what happens due to the density of different tectonic plates when they collide. And here's again another example. You have the oceanic plate here, and the oceanic plate is coming into contact with a continental plate. And again, the oceanic plate kind of gets shoved below. This is called a subduction zone. And again, this is where high heat things get melted. This is the upper mantle, and this is what creates your diamonds. Lots and lots of pressure, and you are creating a diamond field here, in a manner of speaking. So you have in this place here with this particular density, this is good for diamond formation. Okay, so here you have impact crater created by an asteroid. Again, that's creating that high impact is creating high density, packing things together. And of course, you might find diamonds there as well. And here again, the formation of islands, right? We talked about the volcanic activity and how that occurs along a subduction zone. And so here's Japan in 2013, not too long ago, maybe about 10 years ago at this point. So here at 2013, you've got this island starting to form, and you can see this is gases coming from an active volcano. Here you have lava, and that's kind of forming this area here. And then a year later, same island, look how much it's grown. So you got a lot of activity. The lava is coming out. It's creating more rock, more surface, and the island is growing larger. And so again, you get a new island. So up here, there's the island is starting to form, and then you've got this island part here, and then all of a sudden, over time, you still have the volcano there. It is now engulfing the other island that was close by, and now you've got a larger new island that has formed. So all because of the activity happening due to the subduction zone that is causing the volcanic activity to occur. Okay, so that is it for this video. I hope you enjoyed this video. I hope all of these examples of density in the world around us was a great example and really entertaining. If you enjoyed this video and learned a lot from it, then by all means, please like the video, share the video, hit that like button. Also, subscribe to my channel, hit that notification bell, and when you do, make sure you hit that hit all so you can be notified by all the videos I put out. And finally, please put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.